Hi, this is Coffee Compiler Club. Anything to do with compilers? Oh, here's Cameron even now. Anything to do with compilers, language runtimes, garbage collection, concurrency, well, type systems, sandboxing, whatever, it's all good. This is being recorded live. I'll throw it up on YouTube and Twitter after a couple hours or a couple days. Open mic, ask what you want. Reserve the right to moderate, never had to do it. I don't have typically an agenda, so typically we're a little slow to get started here. Let me throw in some new people here, and then oh, more, fine, yes. I just need to start 2 minutes late every day, and it's all good. Yeah, so my 2 seconds of status update is I spent the last 2 weeks doing tech debt elimination and consulting gig stuff. And the tech debt elimination is finally winding down and tests are running again. And so I'm back to integrating Hindley Miller and forward flow typing, which is kind of making good progress now that I'm working on it, actually. So that was my 10 seconds worth of progress. And I'm looking for a topic. Anyone want to start, or I'll bring up stuff from last go round we left hanging?
Yeah, I'd like to bring up a topic. If no one else can bring up the topic, I'll just hijack the entire day, if you don't mind.
It's all right.
My topic of the day is thread scheduling.
Yeah, I'll hijack the day. Okay, fine.
I have to say that I've been running into more and more situations where I guess I'd like to say that we live in an industry that suffers from CPU envy. And that's pretty much all they look at. And I just have these people that are now in these virtualized environments, just like packing it up, right? And they're doing all these weird things, which means you end up with what I just call like a revolving door. And part of the revolving door pattern involves basically voluntary context switching, which means all of a sudden everything just gets backed up on the thread scheduler's ability to keep the CPUs busy. And I don't know if anybody's been experiencing anything like this, or
this is Java.
Doesn't necessarily have to be Java, but yes.
No, it doesn't.
Java. Sorry?
I said no, it doesn't. But that's the common place where you get lots of people who haven't done a whole lot of threading work piling in with strange threading behaviors.
Yeah, and it's really hit hard. I mean, I was just looking at one app, and they seriously could not get. Now here's the fun part, right? They could not get a CPU saturation past 30%, because like when you whack the box at that level, I mean, you just like fry everybody across the board, right? Like really heavily.
H2O would get 100% CPU utilization every time. Fraction of a second, all cores, all time, blasting away.
Yeah, exactly.
It can be done.
Yeah. Well, it's not easy to be done, but yeah. So I'm just wondering if anyone knows anything about anything that's going on, about anybody looking at this, and even the effect of hypervisors, like, so I mean, we used to run a stupid benchmarks, like, sleep for a millisecond 1,000 times, like how long does it run? And you put that in a hypervised environment, it's like, you get like 2x, 3x slowdowns, just because you have a pressured resource that you're now asking to do more work.
Yeah. So like, there's a huge count of bugs that can happen here that people just maybe haven't been dealing with enough. I certainly fought bugs in the Java core runtime, which would be infinitely yielding bugs, where every thread tried to yield to the next guy, and you spend all your time in the yield loop, hot yield loop, and that won't show up in your typical profilers because the context switch overhead doesn't get profiled so well. Wait notify loops where 1,000 threads are waiting, they all get notified, they all wake up, one takes the lock, they're at 999, go back to sleep, and you spend all your time context switching them. They wake up one at a time, reach for the lock, it's taken, they go back to sleep. The guy holding the lock makes no progress because he's got 1,000 people competing for CPU wake up. So there's a lot of these patterns where you know, you have a thread-like thing and you just say, wake it up and then go to sleep, and wake it up and go to sleep because you're competing for locks.
Yeah.
But we worked really hard at this at Azul too. And I don't know, I don't have a good answer. Like there were patterns, there were lots and lots of anti-patterns, and there was some careful work done to make the normal, I took a lock, I released a lock that Java goes through, work well. In the land of H2O, we limited actual threads. This is an early cut of Douglas fork join with a bunch of hacks. You limited the actual thread count to something not much more than the actual CPU count. And then you had a work list of tasks. So it was what you might call, what's the current one? There's one, the Java folks are now doing it for real.
Right, but this is not really a function of the number of threads, because it's really a function of the thread behavior. So I mean, if you have one thread behaving this way, it's, yeah, well, you're not going to see it.
The goal is to not pile in more actual threads than CPUs by very much, because the OS scheduler has real limits on what it'll do in order to keep its context switch times under control.
Yeah.
So a standard. Sorry, go ahead.
I was going to say I could share a bit here. I've been working on this problem for the last 2 years, and this is outside of my ecstasy work. But for my day job, the platform we have, like huge Java JVMs, like terabyte heaps, and hundreds of thread pools inside a JVM, like hundreds of thread pools that don't know about each other. And there's this constant battle of, you know, anybody that creates a thread pool, like what's the right thread count for their thread pool? And of course, there's no way they can account for the other 100 thread pools other than theirs, right? So you get this, like, people way under allocate and they way over allocate. And so you end up with servers that most of the time have tons of threads and yet aren't making a lot of forward progress. So I've been building this system that we call it a unified thread pool, but it's basically, there's a concept of a lightweight thread pool. So it's something that feels like a thread pool, but it has no threads.
Right.
And you build like a hierarchy of these things, and they funnel down to like a core central real thread pool. So the actual number of threads in the JVM is somewhere around core count. And all these other thread pools are basically schedulers deciding which thread pool should now get time.
You've intercepted somebody else's thread pool thing and steered it to yours.
Yes,
yeah, exactly.
Well, Mark,
is that meaningfully different than green threads, a la, say, the Erlang VM, where it's just like, oh, create large numbers of these tiny threads, but only have one thread per OS thread?
Yeah, I mean, I think it's all kind of in that same space, right? There's aspects of this that feel a lot like Loom, although without me modifying the JVM, but certainly not as lightweight as that. But it satisfies the, like, right now in the system, we have hundreds of thread pools and thousands of threads. Like, instead we can have millions of thread pools and, you know, hundreds of threads. And then each one of these thread pools has like independent schedulers for determining task execution. And the other thing is switching to most of them, or by default, they'll use a fair scheduler rather than the simple, you know, traditional FIFO or priority based scheduling. So of course, we're only just starting to roll this out. So who knows, maybe it won't, maybe it won't work well.
The major fail here that wasn't known, so there's regionals, is Java gave every program the right to make a thread pool, which is a system-wide resource.
Yeah.
And no way to acknowledge each other. So yeah, everyone can make their own thread pool, which consumes all their CPUs, and then it doesn't work. And so immediately the thing I had to do in H2O was say, you cannot do this.
So Mark, I'm really interested in this because, you know, one of the things I was thinking about when I was looking at all this and going like, well, you know, the answer is like, you know, you need to stop the revolving door, which means that you need to actually have each thread consume more of its time quantum before it decides to either voluntarily or involuntarily context switch out. And, you know, I was looking at Loom going like, wow, it's a possibility that Loom would allow us to actually pack more work and so that we actually get a thread to consume more of the time quantum and to consequently slow down the rate of context switching.
Right.
At the less level.
So let me head you down this path that we did at H2O, because we exactly had to fight this problem, which is that we have a giant, embarrassingly parallel data set problem. And so you divide the work. How finally you divide the work? Because if you overkill, you get too little.
Yeah.
So I think the first fail is to get rid of everyone has their own thread pool, which is what Mark was saying. Can't do that, or you'll have a million threads and then the OS will just die and it doesn't matter. Everything else follows. Now you have, instead of a million threads, you have a thread pool with 1 per core or 2 per core, and you have a pool of tasks, you have fibers. And now how big do you make your fiber? How big do you make a piece of work? And for us, it was we arranged the effort that we could dial a knob on how hard or how much we could add or subtract work, because we sliced our data however finely we sliced it.
So this is actually worse than that, because it's not a per JVM resource thing that you're whacking.
Yeah.
It's across the box
Right.
thing you're whacking. And you add hypervisors into that mix, and all of a sudden it's like a really heavy whack, right?
So
you're talking about where there's no cross JVM awareness.
Yeah.
Every JVM thinks it has the whole box.
Yeah.
Right.
Everyone thinks they have the whole box.
There you go, Cameron.
So the approach that I took there, and it's fairly minimal, but each JVM tries to make a guess at what percentage of the box is theirs by looking at what percentage of the RAM they got. So if you get a quarter of the machine's RAM, you're going to assume you can take a quarter of the machine's cores, right? So you automatically kind of get into the right space. But then everybody complains when they run on their laptop and they have far fewer threads than they think they should have. But small heaps on laptops. But
but you also only got like 2 cores, so it doesn't matter.
You have an old laptop. But yeah, like the constant complaint we have is like our laptops have 16 cores.
16
threads, right?
Okay.
But
mine's fairly new. It might have 4.
Yeah, mine is 4.
Yeah, I have 8 cores, 16 hyper threads, and I run a JVM that I have a 32 gig machine, and I run a JVM that only uses the max out at 8 gigs. So my ergonomic algorithm doesn't give me access to all my cores. But in the real world, you get much closer, and then of course you add in GC threads and all the things that don't funnel through my big thread pool, and I think it kind of gets you into the right space.
So count away GC threads and JIT threads, because they must run at a higher priority, or your concurrent GC is not concurrent because it gets starved out, right?
Yeah.
And you don't ever JIT code because your interpreter, your JIT thread never gets done, so you always run the interpreter. So you have to count those out. Like, there has to be also a priority. So there is whole box awareness versus inside the JVM. There's per whole box thread priorities that have to happen that are not commonly available in any OS, which really sucks. Because you have to do shit with like visual presentation. There's only one monitor that you're fiddling your GUI on. So some background core goes and does H2O work, doing machine learning, burning all cores at a low priority. I can't have another JVM with a high priority thread demand to use the GUI. It just gets stopped.
I think that priority is at least priority work chosen by humans is a pretty bad thing. Like it ends up very similarly with when I started with 100 thread pools. Like when there's too many people deciding what the priority of stuff is, you're screwed, right? So you end up having to have some single entity come in and prioritize everything, which also becomes unreasonable. So the way that I fight that is, again, like limiting the number of threads to be around core count. So we're never going to overwhelm the OS. And then the priority of individual work items has to be prioritized by some algorithm, which is a fair scheduler, right? So things dynamically change priorities so that everyone gets access. And long run, use more resources so they naturally get prioritized, and UI type tasks, which are short running, use less resources, they tend to get higher priorities.
So Mark, I had some questions about that, or comments. I would say that if you've done something to reduce the number of threads overall, then I would say that I would let the thread competition for the cores actually just happen naturally at the OS level. In other words, let the threads.
Right, but then
because
for tasks in the queue to gain access to that thread, right? I've limited my threads, but now I have a queue of hundreds of items. Which task do I run next, right?
Yeah, so you solved that problem at the JVM level, but you've actually reduced the number of threads that are now the thread scheduler is having to cope with, which means that you're giving threads more work to do. You're reducing, so they're consuming more of their time quantum, which means that you're actually taking pressure off the thread scheduler, which means I wouldn't actually limit the number of cores for per JVM in that particular instance, unless there was a necessity to do so.
I think we're missing a big piece here. The OS doesn't have a way to have you compete marketplace for scarce resource between processes.
That's fine.
So, no, it means that the OS just makes everybody equal, even if you know damn well you need to have something more equal than others.
Yeah, okay. Well, I mean, right now we have an analytic right now. We can see this going on just by looking at garbage collection behavior. Okay, so yeah, I know it's weird.
Well, but no, you garbage collection is an example. If you're expecting to be low latency because you want concurrent GC and you don't have anything to do with thread priorities and you have other JVMs running, it is entirely reasonable that another JVM puts a giant big ass stall on the one that you're expecting low latency on, and you don't get the low latency. So your GUI gets herky jerky because it has nothing to do with GC. It just has to do with another thread is just running.
That's correct. It has nothing to do with GC. It's just that we can see the effects very easily in the garbage collector because the data is just readily available.
Okay, wait, let me address Cameron here.
Right.
Goals to limit software thread count to hardware thread count. At H2O, we had to say to people, don't run 2 H2O nodes on the same piece of hardware.
Yeah.
And if you did, you know, suck it up, Buttercup, things went bad.
That's exactly.
Yeah.
I mean, if you're trying to make maximum use of the hardware, you can't be sharing it with other things trying to make maximum use of the hardware.
Yes, you could share it with something doing a GUI thing, but you can't have another guy doing max use hardware. Yeah, exactly. And what I hear Cameron saying is we have a bunch of guys that are semi-unrelated to each other and semi-related, and they don't really know about each other very well. And some of them try to use all the hardware some of the time, and some of them do, and some of them don't. And so they all overcommit, and they don't have enough work for their threads, but they would if they own the entire box, maybe, but there's not a good way to measure how much work they have per thread. So they end up turning real big, and also they're turning at the OS thread level as opposed to also inside the JVM.
What an interesting analogy.
And you're very quiet, Cameron.
Sorry.
Your mic is low.
I'll speak up.
There you go.
I'll project my voice.
I don't think you have the right mic on.
Oh no. Give me a second.
So is there a reason you can't do a TCP-like thing and say, hey, I'm detecting that I'm churning really badly. I'm going to reduce my number of OS threads. And if there's 10 things that are all trying to balance it and detecting it and backing off.
This is the user
thread count. It's not the thread count that's the problem. It's the thread behavior that's the problem. Like if you have 100 threads doing this or 1,000 threads doing this, I mean, you end up pretty much with the same effect.
It is both problems, Kirk. If you have 1,000 threads and there's been various versions of OSs that have hard caps on the count of threads per CPU, they will reasonably schedule at like 8. So if you have a 16-core machine and you times 8 and you're up to like 64 and you put 1,000 threads on, 990 of them are actually truly starved, not even just poorly scheduled. They are truly starved.
Yeah, okay.
You end up,
I understand, but there's two problems
where they wait for an item and they don't see it and they go to sleep and they wait again. They keep waking up and it's not available, and they go back to sleep and they wake up a millisecond later. It's still not available, and it will never be available.
Yeah, but
if we take the JavaScript VM as an example, in JavaScript, you can have something that it's got its like event queue that it's trying to work down and keeps throwing new things into that.
Yeah.
If you have too many futures and you're like, then, you can get this problem with a single thread that's running all by itself because you're doing like one instruction and then you throw it into the queue and then you pull it off the work queue and you do one more instruction and you throw it into the queue.
And that's because the wake up knowledge in the JavaScript VM hasn't been thought through to be cheap. Like the fork join wake up is infinitely cheap. It's one clock when it happens, and no time do you stare at a job that's pending and not ready to go.
Yeah.
That was a key item. Whereas what you just already heard you say is we have to look at jobs that are pending, but we don't know if they're ready to go yet until we get a callback from the database or whatever. Those should not be on any.
Right. So it's this JavaScript is doing a polling based solution, right? When has that ever been the right way to do things?
Right, because what I really want is an inliner that says, oh, you've got 17 deep callbacks. Can I inline them all and just do this as straight line code for 1 millisecond or 1 microsecond?
No. That's a different problem. That's an optimization problem for the compiler doing inlining, as opposed to one that says, I bottomed out at a network call to a database that hasn't come back yet. So I want to take this pending wad of work and shove it somewhere. And then the difference between polling and wake up is I never, ever look at it until the wake up happens. And the key item there is that I could have 1 million of them pending. Whereas if I'm polling, I check 1 million things and nothing am ready. So I get no work done because that was my time quanta.
So I just wanted to clarify one thing, Cliff, is like, in terms of thread count and work behavior, like we're dealing with 2 problems. Like you can starve the thread because you have too many threads, so you're competing for the CPU, right?
Yeah. Yes, that's one, yes.
Yeah. So you can exacerbate that problem by having threads that are using only a fraction of their time quantum.
Yes, I agree. There are 2 problems here.
Yeah, so it's 2 problems.
Yeah, I was hearing you say 1, but there are 2, and they're both real problems. Yes.
Yeah. So I've only really been focusing on the 1 problem, which is like the threads are now so well optimized that they're only using like minimal fractions of their time quantum.
Yeah.
The system is balanced to for threads to actually use the time quantum.
You need to increase the amount of work per thread. However.
Right, and that's what Loom promises to do.
Okay. Yeah.
To just to keep touting my my solution to these problems. So the way that I did that was tasks can be cooperative, and a cooperative task is given access to, or minimal access to, the scheduler. So they can actually turn around and ask the scheduler, should I yield? Right. So they have their quantum, but like they don't have to blow out and context switch just to be run again instantly later. Instead, we say, like, do you have someone who deserves the CPU more than me? Nope. Okay, I'm going to keep running.
At H2O, we had to do priorities. And so we did it with user mode, voluntary preemption on priorities. But we had priority tasks. And so if a low priority thread woke up, he first checked if there was high priority work available. And he then declared himself high priority and did it right there. It was basically user mode priority settings, but it was done with voluntary thread at every micro task point, deciding he up-leveled himself.
Awesome.
And I did it with polling of the higher priority queues, which sucked, but I never had very many priority queues, so there weren't too many levels of priority, so it wasn't too expensive.
Yeah, I went the route of well, not a red-black tree, but basically I have a single queue that is prioritized, but not by any fixed priority. So every task computes a dynamic priority when it enters the queue. So I never have to go and check 8 queues, right? It's always just check the head of the single queue for that executor.
So, okay, wait. I get a packet over the network. Some IO thread, which is not part of my worker, his only job is to eat the IO. Eats the packet and throws it on a queue. And then he goes back to staring at the network and sleep until it happens again. So tasks apparently appear on queues arbitrarily. You're keeping a priority queue all the time and sorting it.
Yeah, it's always a priority queue, and it's sorted upon insertion, right?
That I had to sort on, which was a task might block, and it eats the OS thread when it blocks.
Yeah.
And then if he's eating that OS thread, you had to spawn a new thread. But if every thread blocked waiting for something else, no matter how many OS threads you had, I had millions of tasks to billions. They're just coming. You would run out of OS threads and die. So I must have priorities, not for performance, but for correctness. It's the same as lock ranking. It's just identical behavior to lock ranking, except it goes around cycles in a cluster. So one thread can have an IO task blocking, waiting for some of this that guy, circle
How
around.
did you have IO tasks blocking? How does that work?
Cameron, you're too quiet to hear.
How can you have IO task blocking?
Yeah, a guy is doing machine learning. He is walking a giant pass array doing stencil calculation. He comes to the edge of his piece. He needs the piece from the adjacent chunk of an array, which doesn't fit on this node, so it's on that node. So he says, please, Mr. Node over there, tell me the edge piece of my array over here. Something like that. There are lots and lots of these places where I had to go get something from that guy over here and make progress over here. Because data volume issues, I couldn't keep it all locally. I did a bunch of work to cut that down, but it was always the case it happened. As soon as it happened even once, you would have this cycle go around the cluster and you would hang with a spin. Everyone in the cluster is waiting on somebody else.
Right, so then you have to compensate and add threads.
So Doug Lee Fork Join has this managed blocker thing, and he'll tell you he's going to block. So you stop and you bump the count of the pool you're in, but you only block if you're going to get a response from something that's higher. Like the thing you block on is immediately a higher priority than what you are. So if I'm doing a local calculation on a node in a cluster, and I need something from my neighbor, the request I make to my neighbor is guaranteed one higher priority than I am. And that has to circle around so it gets back, maybe even gets back to me, blocking as we go. The same machine, but that priority only gets bumped. Does that make sense?
You're bumping the priority of the new work that's coming in?
The new work that's put on a remote machine got bumped. I say remote machine. The new work that gets waiting on another thread, wherever that thread is, here or there, is always one higher priority. It's lock ranking all over again. If I have to block waiting for a resource from somebody else, that resource gets my priority +1 as a minimum. And that has to go around the cluster as well as across threads within a cluster, within a machine. It's an old school.
What stops that from counting to infinity?
You have to design your reasons for bumping such that you don't count to infinity. So stupidly, I say it's one higher priority, but what it actually is if you're asking for something that's part of the task I'm currently in, but you're on a different node, I can ask that other node because I know the no one over there can circle back to me because I know the data is not cyclic in that nature. So it doesn't actually bump except conceptually for the calculation I'm working on. But somebody else might be waiting for my calculation. So I'm computing a min of a vector that's distributed, or a max of a vector that's distributed. And I have to get something from my neighbor after a while because I needed his max to make with my max. And I know these things are log tree distributed. So there's a breakdown that's log tree, but I don't have to bump priority because within that calculation. Somebody else is doing a gradient boosting machine and he needs to know a max and min of a column. So he's asking. He's blocking, waiting for the min to max. So the min to max got bumped 1 from the JVM state and so on and so forth. So there's always a limited count of these based on algorithmic description. Same as lock ranking, you had to decide what the ranks were and limit the count. There had to be a limited count or you counted to infinity. And I had bugs where I counted to infinity and ran out of threads and died. So we eventually got it down to where we routinely needed 4 or 5 priority levels, and certain algorithms occasionally went to 10. Nothing went to 100, but maybe
you needed fibers and non-blocking IO.
Well, it was all non-blocking IO. If I actually had a real non-blocking IO, it would have saved me in the sense that I wouldn't have to have to manage block hack. But you would still get the case where you would block infinitely without prearranging the levels of blocking. Like if I had to block from a neighbor and he blocked and I didn't do the priority hack, I just had millions, I kept blocking. Eventually, I had millions of real threads, it would work, except the cost of spiraling around the cluster with a network packet per spiral around going millions would be excessive. So it had to be the case that I had an intelligent limit, and it was easy to define. You know, once you figured out that you had to do it, this task.
And it wasn't that you defined a limit, right? It's that your algorithm ensured that you would never go beyond some reasonable.
The algorithms
number?
were right. Basically it boiled down to one pass over a vector of data which was distributed would only ever bump you one priority level. And if I needed an answer that required computing something on that vector, then that was the one priority level. But if I was computing something on some set of vectors or a vector and somebody else needed it from me, each one of those was one, but I only had so many vectors of data. So every individual computation on a vector times the kind of thing you might compute on it, you could worst case scenario your way up to 50 or 100. It wasn't, you would have to try hard, but there was no theoretical upper bound per se. It was algorithm dependent. Like people did hyper parameter searches over large ML platform things. The hyperparameter search might be 5 layers. The individual run of a deep learning or JVM might be 5 or 10 layers, and they internally leafed out at doing minor histogram calculations that were a couple more, and you ended up with 20 or 30. I'm gonna keep raising my numbers, but it never was huge.
So if you have a graph of data, you get into trouble if there are cycles. So you have to build some kind of spanning tree. And because your data is a giant vector, your spanning tree is just the natural tree that is the data. So spanning tree is free here.
Yeah,
and the depth of your tree is your max possible priority.
Yeah. As soon as you have cycles, you must break them with some technology. Spanning tree is fine. Yeah. Otherwise, you have the I'm waiting on him, who's waiting on, and as you say, you walk through the graph until you die. Well, or you don't, but it's super inefficient. Crazy, stupid, inefficient. I guess technically it can be made to work. What's Matt's here saying here? Yeah, throwing, okay, right. So York, counting.
Yeah, that was just a comment about it, particularly if it's CPU driven. Like obviously if it's blocking on IO, you can start tens of thousands of threads. Doesn't really matter. But it's more if you have 1,000 threads aggressively competing over an 8-core CPU, reducing that from 1,000 to like 800, it's not really going to make a difference. But if you reduce it from 1,000 to 6, now you suddenly have 2 extra cores. That was right. The point.
You have some easy swap, so it's not hard to hit the sweet spot, but you have to hit the sweet spot. So I think at H2O we said our target was double core count for OS threads, but never more than double OS threads. And we profiled a bunch and didn't get any more CPU utilization per se. We also didn't have Kirk's issue of really tiny, too many guys with really tiny amount of work per.
Yeah, a revolving door.
We forced, right. We failed there a number of times and we backed that off. And again, the sweet spot's big, but you have to aim a little bit.
Yeah, I hate to be pandemic on the language, but this whole idea of threads competing for cores to me is sort of, I mean, I understand the language, but the idea that it projects is sort of backwards to what's really happening. Because you have like a thread scheduler that's selecting among threads. I guess that's a competition in a way, but it's really, the threads don't really have a say in it. They're just there. They present themselves. It's a thread scheduler that's doing everything.
Yeah. Somebody maybe puts a priority on it.
Physically, it's just that when you get into conversations with other people about the problem, it's one of those things, if you say it that way, you get some really strange feedback when you come to them a couple of weeks later and they tell you all these weird things. And whereas you try to say, no, if you sort of explain it the other way, then you tend to get a deeper understanding. Is really weird because, in one customer, they basically, here's what they did. They took, they deployed, they had the problem. They said, oh, garbage collection is always a problem. So what do you do with the garbage collector? You give it more memory. They gave it more memory. And in the process of giving it more memory, in order to fit everything on the machine, they had to evict a JVM out of it, right? Mm-hmm. They got better performance. Surprise, surprise. They think it's really cool, but now they have COGS problems because memory is high, costs are higher, and they're looking at it and go like, okay, so what do we do now? How can you reduce our memory footprint? And you look at it and go like, yeah, not an issue. You tricked yourself into, right? And so we go through the process, we drop them back, crank their heap size down to about 1/3 of what it was. And so what do they go and do?
Put
They're
the
going to say, oh,
JVM back.
now we can repack.
right.
And you're going like, face palm, no.
Right.
Smaller machines, don't repack, right? And really it's like, you just have after you've had these discussions with a number of people in different groups and different situations over time, you realize that people actually think the threads are competing for the CPU, and you're going like, no, that's not what's actually happening. They've presented themselves as somebody is selecting them. So in that way, it is a competition. So if you have 1,000 to select from, then of course, that's different than having 100 to select from. But that's a fundamentally different problem than having this revolving door issue.
Yeah. No, you have to address both. And the problem of having multiple JVMs on a box, same hardware, is they don't have any way to communicate to each other to cooperatively present effort to the OS.
Yeah, but just reducing the threads per one, like what Mark has done, is going to help the situation, just because you're reducing it and you're bulking. You're reducing number of threads and you're bulking up the work per thread.
Yeah, okay, fine. What I heard Mark say was he's reducing the count of OS threads by forcing people to funnel into one thread pool, but individual threads only pick up more work per quantum if they voluntarily announce that they are available to do that.
That's in his thread pool though, right?
I'm sorry?
Mark? That's in your thread pool, Mark.
The thread
sorry, what was?
They're not voluntarily announcing, they just get work. I don't think it's voluntary.
No, some thread is doing a task. The task could be much less than a time quanta. He checks some bit, it's not available, he goes back to sleep.
Okay, gotcha.
Right. So yeah, I mean, there's multiple things going on here, but when you have a task which has the idea of I don't have to finish everything before I stop, right? So I can yield.
Mm-hmm.
Right. There's the kind of simple thing, which is like, we see it all the time where things will like, oh, well, I've run for 5 milliseconds, I'll yield. But maybe there was nothing else waiting on the thread. So now you've yielded and pay all the costs of yielding only to immediately be rerun, right? So there I give those tasks a way to call into the scheduler and say, hey, scheduler, do you want me to yield? Of course, that's completely independent of how many threads should we use inside this JVM. Right.
Right. Okay.
This
cool.
is calling yield.
Are you?
Well, it's not calling yield. It's the should I pretend that my task is done, right? Should I pop the stack so this thread can run something else?
All the semantics of calling yield.
Right. Yes.
In sort of the user written hard work loop has a voluntary yield point.
Yeah.
And I have seen so many bugs at the Java layer where somebody tries to do a yield because they're getting clever about spin locking, and they just turn it into live lock because they endlessly yield. Fine, but that's separate. That's an unrelated thing. Never mind. Sorry, Kirk.
No, it's okay. I was just asking, Mark, is your project in a GitHub thing that we can look at, or is it?
It's
firewall?
not, but I've been asking and told that at some point the lawyers will approve that. But no, it's unfortunately not.
Right. Understood.
Start it outside the lawyers with the clear description that it's not company. The next one. I learned my lesson a few times on those.
Yeah. So yeah, we're trying to evict some software into the open right now. So we're almost at the point of lawyers, but we've had to do some other first. And it's just
I started
in the first place, it's shitload easier, right?
I wish that was something I was able to do. I started that conversation 2 years ago when so Doug Lee had put out on the concurrency list, like that, they were refreshing the lock implementations in the JVM, and mentioned like, the only one we really weren't able to improve was the read-write lock. And I had just finished writing a read-write lock that was way freaking faster for read acquisition than the JVM one. It's like, oh, gotta get it out there. And 2 years later, still don't have permission.
What'd you do for a faster read-write lock?
So the approach that I took was to, one, like, I don't care about writers. Like, if you're using a read-write lock, it's because you have a lot of readers. So read acquisition needs to be the thing that you optimize for.
Right.
And so acquiring the read lock is like, basically the read-write lock is backed by a single atomic long, or most of the state is. And acquiring the read lock is literally the increment and get, right? It's not let's not use a CAS, it's an actual increment and get, right? So like there isn't failure, right? That was like a big advantage from doing increment and get rather than CAS. And of course, most of the time you increment and you can look at this at the state after the increment and say, oh, it was good. Like there was no writer. And the fact that I incremented it has now prevented any writer from taking the lock.
Right.
If you incremented and then looked at the post state and saw that there was a writer, then you have to like back out, and that's more expensive. But again, I'm optimizing for the case where it's high read contention or many readers.
So
and then
increment and get a CAS?
No, but it's a
no, it's a hardware instruction.
Yeah, on an x86, it's an atomic.
Okay.
On other platforms, it's implemented as a CAS.
CAS, yeah, okay.
Right.
No,
CAS can fail, right? Increment and get can't fail.
Right, and it's implemented as a CAS with a loop.
On other platforms,
On
right?
other platforms.
On x86 and like any platform we care about, it's going to be
is there
an actual instruction that can't fail.
Is there an atomic?
I think so.
Okay,
so.
I don't know.
But yeah,
Okay,
I don't actually care about ARM yet, but I will care about ARM.
Okay, we have a serious question here. How do you handle the case where there's an infinite stream of readers? They just starve a writer out.
No, so when a writer comes along, they will CAS in an intention to take out the write lock.
Right.
And that will prevent any new readers from being able to acquire, and then they have to wait.
Okay, now
and then the other, I think the other significant optimization was like the locks have to be able to be reentrant, and the way that the Java read-write lock works, has a fast path for a single reader that it avoids doing the thread local cost. But as soon as you have two readers, that fast path goes away. Like the second, third, and fourth reader, they all pay this huge cost. And mine basically is able to maintain a fast path reentrant lock for all, or reentrant count for all the readers. So like it was something like on my 6-core box, it was 6 times faster. Like it scaled linearly out to core count.
I did reader writer locks for Azul system, so we had to do 1,000 core boxes. You couldn't CAS one word with an atomic. You couldn't do an atomic increment of one word where you had 1,000 real CPUs trying to CAS it as a reader because you wouldn't.
Yeah. Well, I took the same approach and then made a parallel version of the reader lock that works similar to the concept of the what's it called, the long adder.
Yeah, long adder.
So it's striped, right? So again, as long as there's only readers, you're incrementing in your partition. And of course, writers then have to take a write lock across all partitions.
Exactly.
So infinite scalability there, but
I did that damn thing at Azul, and I told Doug about it, and he got that from me. And it's in non-blocking hashpick repository. It's called concurrent auto table. It's that damn resizable counter array, and exactly the reader writer lock was done that way.
Oh. So you're
but the Java read write lock. Well, I don't know.
No,
the Java read write lock.
My version
is lacking.
that went exactly what you're saying, spread it hugely wide to let the readers all increment a different cache line. You have to increment a different cache line.
Yep, exactly. Yeah, so it's all padded and everything. And then so I have that in my software repository too. But then I had to start warning people because all of a sudden everyone's like, "Ooh, scalable read write lock." I'm like, we don't want a million of these in the system because they take a huge amount of memory.
Grab concurrent auto table out of non-blocking hash map and use it as an open source base and finish it out as a read writer lock. I did it for Azul. I just didn't bother to put one in non-blocking hash map because
I did take a look at that.
Shit, x86 was 4 cores, 8 cores. Now that we're all 16 and 64, it's worth it. Yeah. So good answer. That was one to know if you did anything different than what I did. And the answer is no, I did about the same thing.
I got slightly lost there. So the readers are incrementing the data structure?
The reader the rule, the issue is on a very high count of readers, they will block each other because you cannot have them all atomically update anything under any hardware model on the planet unless it's shared, not shared, it's parallel. So they have to be independent cache lines for a high count of readers. The other thing is on an x86 specifically, there is a locked add instruction, which will do an atomic add that will not fail. Other platforms will do an atomic add with a CAS that fails, and they'll just loop and add one and go again. The fail rate's low, but it's not very expensive, so you just do it that way. Fine. So there is an atomic add floating around. So the reader wants to take an atomic add. Having bumped the counter, that tells somebody that the reader intends to go in. He can now look to see after the bump if the lock was now right locked or not. So he just bumps the count saying, I intend to go in. Then he tests to see if it's currently right locked. If it is, he has to go a slow path thing, which he probably unbumps his count and goes on a wait queue, waiting for the writer to let it go and goes to sleep. Fine. If you have 1,000 readers and a rare writer, the readers all don't want to bump the same word because of cache contention, whether it's an atomic lock on an x86 or a CAS or whatever. You just want to bump the same cache line. So now they bump different cache lines. So you make a big array and you pad it out, and everyone takes a random die roll and they pick one, they increment. Fine. Now what's the writer do? Well, under the old model, the writer would come in and flip a bit, maybe with an atomic add, saying, I intend to write, and then he'd wait for all the readers to disappear, and then having them all disappear, he would now do his thing and then wake everybody up and go. But as soon as you have an array, what do? Well, he's the same thing, except he does array element by array element. He walks the array, and everyone only picks one element per cache line. So he strides the cache lines, sending his intention bit one at a time across them all. Then he goes back and looks at the cache lines to see if they're all cleared out. And if they're not, he has to wait. And now you get a question of, do you spin loop, or do you go to sleep and the last reader out, when the reader notices that he's leaving and there's an intention for a writer and the count went to 0, he bangs the writer on the head and says, wake up. You do something like that. Then you have multiple writers that want to come in and they want to go set the right bit, but it's already been set. So they have to go queue up on a list of writers. And there's an efficiency thing where you say, once a writer got the lock and you're piling on readers because it's infinite, all the writers go one after another sequentially in order, because that's as fast as you can do that. And then once they're done, they flip it back and let the readers go again. And I went all around these things, a bunch of different directions to get them fair and efficient. You got to do fair too. So there was another rule about fairness, which says if a writer came in while the one writer was writing, maybe you would let them pile up. But at some point, a reader came in and the next writer had to wait till this reader went. So you got a multiple deep queuing of just one extra of all the readers that were pinning behind the current writer holding the lock, and more writers that were pinning behind those readers in order to get fairness.
There wasn't an issue with starvation, like in JDK 6.7, like you end up with, I think one ended up with reader starvation, the other one ended up with writer starvation because of all this?
I was trying very hard to prevent starvation in both directions for high flow rate, high core count machines. It was a lot of work.
I think I went with the route where the default like fairness mode for the read write lock was that it just oscillated. Like, oh, I last serviced a writer, well, this time I'm gonna a reader over a writer and just flip back and forth.
That's what I was trying to do, although I didn't have it as clean as an oscillation. I had to have.
Yeah, I mean, I think it was a like, it should be around 50%, but it wasn't, I didn't make it, pin perfect. It was just like, we don't want to just always go readers or always go writers.
Yeah, you can't do that or you starve. Right. That was the fail that I had to sort out.
Yeah.
And
same theory as a traffic light. You let a whole bunch of cars go in one direction, and then you let a whole bunch of cars go in the other direction because there's switching costs.
Right. Yeah, and in fact, the other one is if you have a steady stream of writers and you sequentialize them, then Amdahl's law kicks in and no one else gets anything done. The writers are all queued up anyhow, and the readers never get a turn, so you had to alternate. Yeah, fine.
This whole thing is like just blowing my mind out. It's like, how the hell do you manage correctness and all of that when you didn't really guarantee order of readers and writers and coming into this? And
yeah, you don't mean correctness of the lock behavior itself, but correctness of your application taking a reader writer lock.
Right, because you don't really have any guaranteed ordering of anything happening at that level.
So
if the reader goes in, is it going to read before or after the write? And if he reads before, what does that do?
You have a concurrent writer and a concurrent reader. They are agreed they're going to take a lock and read a read or write independently of each other, but there's no ordering between them. Where is your ordering guarantee now? Independent. Don't say 1,000 of them. You just got one each. One writer, one reader. They're racing for the lock. Might as well be a regular old lock because there's only one reader and one writer. What's your correctness? So however you get correctness there, same issue, just scale it up.
Yeah, that's really been, I don't know, when I look at all this thing, I'm like, yeah, it's an interesting problem to solve. The question is, my question is like, how useful is it? Because, as an application developer, I look at it, go like, oh my God.
You can't use this as an application developer. An application developer should never, ever, 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 ever lock anything.
Yeah, exactly.
Oh, that's a good point.
You
That's
never,
a-
ever, ever lock
If an
anything.
application does anything with locking, the application is by definition wrong.
Yeah.
I would claim that I would call things applications that involve
No.
locking long ago, but maybe what you're
No,
thinking.
I think is that just no one here writes applications, right?
Yeah, could be.
I
No,
do,
back
in
but
the
I
day,
don't
it was
write
all
locks in
applications.
applications.
I actually do write applications. Well, I mean, I guess we write tools, right?
Right. So suppose you're busy writing a thing which is tracking people's vacation. Every now and then somebody says I'm taking a vacation and they update the amount of vacation hours. That has to be a writer thing. 99% of the people are just reading their vacation hours without updating, and they just want to blow through. And where's your correctness? Well, they're all independent actions. That's the correctness.
Yeah.
Yeah, there you go, Matt. So read the chat from Matt here.
Yes, absolutely. That is the way to go.
That is one
Everything easier.
interpretation. That is one interpretation of what I said, but it's the wrong one.
Awesome.
Can we quote you on that?
I mean, yes and no. There's a bunch of stuff from a user perspective that I want to feel atomic. I ran my SQL query and it read a bunch of things and did a bunch of calculations and wrote some stuff back, and that either happened or didn't happen. Like,
Right. Now,
my SQL statement should be atomic.
If you're a database implementer, under the hood, you took a bunch of locks and unlocks. But are you an application developer? I just come as just a jargon name. We're just arguing over terminology here. No, I'm a database developer, not even database, what do you call a systems developer writing a database? What do you call the person who's writing the database itself, not writing in the database? Right, the whole point of the database is to let the database user write lock-free programming and have atomic actions. That's what SQL is all about, right? So the SQL writer is a DB writer. DB admin is something unrelated. That's performance on the DB and backups and whatnot. Then there's a database writer, developer, right? What's that person called?
Client?
No one knows. Fine. I'm talking with a company that's doing that now. So it's interesting to pick names here. Having heard the theory that if you're application developer, you're not writing locking, what do you do? Guy, you do JavaScript. It's single threaded, except we all know that it's not. And so they all have to deal with the pyramid of doom callback messages and stuff. And everyone gets there's locking going on, or your pyramid of doom sucks. And
show me a language that was designed for anything other than a single threaded von Neumann architecture.
Well,
Erlang?
SQL and Prolog declarative things are all about we're independent from the execution model so far removed.
Right. Yep.
That we don't know performance from a hole in the wall. So
I think Erlang's a good example. Probably about the only one.
These guys is relational to AI guys are trying to do declarative queries and replace.
I'd also argue Pony.
I'm sorry?
Pony is also a language that sort of started from this assumption of there may be more than one core in the world.
Yeah, so Pony, Elixir, Erlang, yep.
Well, I'm saying Prolog, which completely abstracts the concept away of imperative programming and CPUs. Right. So, and SQL as well. SQL is a declarative language. It does not have a concept of an execution model per se. A query exists, manifested wholly, and has an answer which is magically available to you. But there's no forward flow if then else per se in that way.
I think GPUs in that sense
Try to do
are
something
similar.
Sorry, York, I missed your opening.
Sorry.
I think in this case, GPUs and whatever languages typically compile down to GPUs are somewhat similar in that sense. That isn't like a single thread. Like you have, thread.
Oh,
you have.
You're saying there's multiple cores. There's parallelism baked into the language.
Yeah, and I think, I mean, obviously it's going to depend a bit on the language, but I think generally it's due to the workload that you would use GPUs for. There isn't really that sort of same linear flow from a program. It's, top to bottom essentially.
Hmm.
But it's maybe sort of cheating because it's a very different purpose what you do with it basically.
So APL, a programming language, was all about arrays, and you implicitly had parallelism on the array operations.
Yeah.
Interpreted linear forward normal language with bulk array operators. H2O, basically bulk array operators on standard forward flow coding.
The GPU's comment, I think I'd describe it as massively parallel, and they're typically most applicable to situations where there's no conflicts amongst those operations that are in parallel. So the APL comment would work well on a GPU.
Yeah.
A thread
So,
do each element of the array.
Yeah.
Cliff, are you going to write an APL front end to H2O?
It wouldn't hurt. What we did, and I bailed out of H2O like 5 years ago. We had an R and a Python front end where we just replaced the things that in R or Python, which would look like a standard array, with a network connection to H2O, and it was turned into a bulk array operator. Like you would have bulk array operators in Python anyhow, people did. And you could write things that did bulk array things, and we would just forward them to H2O. So not APL, but Python.
Yeah.
Nah.
Yeah, APL is much more expressive. Oh, look at that. You can still get APL keyboards. I just did a search for it. I was wondering, like, could you even get a keyboard to support the language? And here it is. Yeah.
Okay.
APL keyboards.
Not ready to go there yet. Be pretty hardcore. I guess if you're like hardcore using it and you got a good experience going, throw down $100 or $200 for a keyboard, fine. Just
I'm just wondering, like, if you think of like quantum computers, like it seems like anything you want to do in that area, you have to reduce it to like some matrix vector thing. So I'm wondering.
Yeah, I don't think we're ready to do wide scale user programming of quantum computers. Like we don't know how to program them yet.
Yeah, that's right. Wouldn't APL be a good language for your quantum computer?
I don't think so. Because APL was single thread of control forward flow, except that each of the operators was typically based on arrays, of which could be very large and parallel under the hood. But I think quantum computers have a completely different concept of what you want to go do things with. They're more like Prolog, where you state a query or a set of facts and the answer just appears without an execution. That's my current week.
But you still have to reduce everything to some sort of like matrix representation.
APL you do. Quantum.
For quantum.
I don't know anything. I don't have that much depth there. I can't say.
Right. Yeah. I mean that's my understanding. When I looked at it, it's like, okay. So as long as you can reduce it to a bunch of vector operations, like everything seems to flow very nicely, in which the APL seems quite well suited for it.
But
if you can express your problem as surface minimization, a quantum computer will work well.
There you go.
The key is to compile your problem into a surface minimization.
Okay, fine.
There you go.
Or maximization. Science better.
Yeah.
Well, it's a matrix.
Surface minimization doesn't have to be any sort of classic, square grid array matrix.
Well, it doesn't have to be square. So,
at some point I don't call it a matrix anymore. Okay,
No.
I think we're well down the weeds of where we're talking about what we don't know shit about.
Yeah, exactly.
Go pull it back in here. So somebody's talking about GPUs and somebody's talking about stream.parallel.
So I still had questions about how you inline when you run into the problem of I have a giant stack of futures that's like do A, then B, then C, then D, then E, and they're all lambdas and they all have like 2 instructions in them.
Right.
But what I wanted to do is actually compile all that into a chunk of code that is worth scheduling.
So I fooled around with the coding style at H2O a bunch. And I recognized that that was sort of an issue, and we manually did it without any compiler support, and you could screw it up and it would be painful. But
So the answer there is write better code?
No, you needed compiler support in a big way. So you know, low latency for all the H2O, a run of a big machine learning pass for H2O doing hyperparameter minimization, blah, blah, would make billions of messages, billions of tasks. So not millions, but billions. And so you just had to have super low latency going them all, and you wanted to have a minimum quantum for them. So you didn't want to have like trivial do nothings. So it was the Dudley fork join model, which was you forked a task and each task took half the work. At the join point, the first man in would CAS saying, I'm done. So there was a word they shared at the fork time that said, I'm sharing some work here. At the join point, the first man in said a bit, and then it was done. His half was done, but he couldn't work more on that task. So he would go back to the thread pool and try again. The second man in would see the bit saying, you're done. I'm not going to context switch. I'm going to flow in, right? So the series of forks and then joins, you get a tree out and a tree in, would have the tail end look like test a bit, double my size, because the other half's done, and now do the tail end piece of work, which is typically a reduction step for the two pieces, which was a small constant amount of work based on whatever you wrote for your reduction, and then test a bit and repeat. So you had a while loop. This is while the bit is set and I'm rolling up the log tree. I test a bit, took the other half, did a reduction, while test a bit, did a reduction. But the test a bit was 50-50 which way it went. So an x86 wouldn't predict and whatever. And it was, you know, it was an ugly loop, but it was also the reduction step at the end. So you wound it down and that would turn into one entire vector worth of work that you got an answer out. And now whatever your algorithm said to go from there, but we didn't get huge stacks of nested futures, maybe because of the priority queuing work I was doing to force you to not do that, because I didn't, it was buggy if you cycled yourself around the cluster and ran out of hardware OS threads, and it was performance suck if you just had infinite number of tasks. We didn't run into that problem because I think we engineered our way around it. Or I should state, we fell into it several times and then engineered our way around it to avoid falling into it. And maybe the right answer is, if there's a way to lift what I did at H2O up into a more general context. As soon as you have futures that depend on future and depend on future, how do you peel out an inline? You know, the JIT could be taught about that, but I don't know that's necessarily yet the right way to go. I applied a higher level invariant and got around the problem. And I don't know how generic my solution would be. That's a good point.
The generic there seems to be check if you're waiting on anything, otherwise just keep going. You don't need to yield at every point that the programmer said it is acceptable to yield.
Yes, there was.
Just fall through if you can fall through.
I took Dudley's solution, which was check a bit and flow through. Right. And that effectively made you switch tasks. So you got your quanta refreshed. That was the sort of the thinking behind why it was legit. You just took the next quanta because it was ready and you were done with yours. Boom. And that was a clock cycle, test a bit and keep running. Yeah, I don't know. The whole JavaScript callback stack of doom thing kind of annoying. Elm did a way to restructure that with state machines, but you had to write the state machine. You got a lot of language support to write the state machine, but you had to write the state machine. It was a pain in the neck to write the state machine, even with all the language support. But it got away from the pyramid of doom and the endless nested futures. And could be very efficient too, because it got rid of that nested stack of futures. But your state machine coding now. Yeah, I don't have a good answer there. Maybe there's a better way to write state machine codings. Or just acknowledge the compiler will make the state machine for you and it's going to make one and you're just telling it, here's where the breakpoint is. And now add another state to the state machine. And then the pyramid, for execution purposes, the pyramid of doom of futures goes away.
Yeah, I think here the answer is to bake it into the language, because kind of what we as in in the stream channel, you can see is if you try to sort of put it in as an afterthought through a library or some extension of the language, but it's not like fully baked in from the start.
Yeah.
Somewhere down the line, you as a developer have to deal with these stacks of I'm waiting for this, which is waiting for that, which is waiting for that, etc.
Yep.
And you have to do something like Erlang, Elixir, probably plenty of other. Oh, I would say any language that is either that or has auto parallelism built in.
Yeah. H2O.
Wouldn't you say Loom is now the solution? Right? You shouldn't use endless futures.
I'm not familiar with the specifics of Loom, but any language, for example, where it will auto-parallelize, well, not so much auto-parallelize, but it's parallel by default. That's maybe the better term. There's a language that comes to mind where I think the logo is like a raptor or something. I don't remember what the language was called. But in these languages, typically everything is parallel unless you explicitly tell it not to.
I guess I was thinking not that Loom is auto-parallel, but when you have a chain of futures, that's basically your individual statements, right? And Loom says, no, like just write your statements and I'll decide when to yield the lightweight thread.
Yeah, basically. I would say that if you, I mean, it's unavoidable to have a construct where you say, hey, wait for this computation to finish. But basically, if you have to manually specify things like, oh, if I do this, then you have to do that, whether that's callbacks or something else. I think that's where you're sort of heading towards a ravine, basically.
Yeah, yeah. At H2O, we manually did it, and it was difficult without compiler support, but you get really great performance. And Elm forces you to break your computation up into a non-sequential state machine with a lot of language support for the state machine, but you're writing non-sequential code of what you think about as sequential. So I don't particularly like either solution per se. I'm with you. There's a better way. Would just have some sort of lightweight thread or I don't know what. But I also think there's some, well, okay, never mind. Fine, go ahead.
I think it's like it's a natural evolution, I think, of language because we started with, single cores, single CPUs, etc. And at that point, all these things don't really matter because, there's only one thing you can do anyway. But hindsight 2020, I think a lot of problems could have been solved if we had basically developed multi-core a few decades earlier.
It's been around a while. It just wasn't performant enough. It wasn't until we ran out of single core performance that people wanted because it's too hard.
Put it this way, multi-core for the average person. That's maybe better because I know multi-core as a concept has been around for quite a while, but I think it wasn't until like halfway 2000s that you could buy, a laptop that had 2 cores, for example.
Right. Now you're developing
one that didn't cost like 20,000. Let's put it
the reason it's here is for obvious. It's difficult to reason in parallel. You get 2 people to finish a job at half the time. It takes 1 person to do the job. That's hard. Some things we've known how to do. You'll build a house. You got 100 people to go build a house. So if you got 2 people to build a house, you can run them in parallel. You got 10 people to build a house if they got the right kind of skills. If you have to keep rotating people, that didn't count though. You got 100 people, they can't build a house 100 times faster.
What's the quote from Mythical Man Month? That it's really hard for 9 women to have a baby in 1 month.
Exactly. That's not the one from Mythical Man Month is, adding more people to a late project makes it later. But the other one is, that one's been around a long time. Yeah. If it takes 1 woman 9 months to make a baby, how long does it take 9 women to make a baby? Well, 9 months.
The problem these days is you have to reframe what you're trying to accomplish as building 100 houses, not 1.
Exactly.
So then you got 100 people, they'll build 1 house each and you'll get them done at the same time as it takes 1 person.
Right. Same as the woman and the baby, but you get 100 and not 1, and then that's the problem. So as soon as you want to get, half the time, You have to have fine-grained communication, and that's the hard work that we're all trying to negotiate our way through.
It's also something we have to do. One computer can never be a reliable system because if it fails, you're done.
Okay, fair.
So if you're going to build anything that needs to be a reliable up 5 nines at a time system.
Yeah, I'll start by going down that path. I'll be a really quick one, which is the machine that sits next to me on my desk has been up for 3 years without fail. Okay, but
I thought you ran Windows.
I have a Linux box running a server that's been sitting here quietly as a notebook sized machine for 3 years. But as the largest single point of failure is almost always these days software. And so as soon as you have multiple systems that are cooperating for a solution, the effort to get them to cooperate well and take failover is hugely more than running one machine. So if you're looking for reliability and you don't have a big problem and you're willing to accept reliability limits at hard fails on machines with no moving disk drives and power outages, you're way better off with one machine. So you said 5 nines. Okay, to actually get 5 nines, you have to have something more reliable than a typical power to your house, right? The data center power has to have a backup plan that actually works.
Yeah, if I need 3 nines, server under my desk is a solution.
Well, that's what I'm saying. So do you really need 5 nines? There are a few places where you want really badly 5 nines, but not very many. A lot of people claim they want 5 nines. A lot of people live, we lost Google, for a couple hours some months ago. We lost half of Amazon. Amazon had half the coast outage for a while. The world did not fall over, but that blew their 5 nines for a decade, and the world did not fall over.
Picky. I mean,
sorry?
People are just too picky. You can get 7 8s really easy.
Exactly.
Yeah, and my 7 8s feature 3 9s.
Redundancy.
No, people seem to get mad at Twitter when it's down.
Yeah, they do, but that's not putting Twitter out of business, and it's not killing anybody. We want 5 nines on bridges, right? We want our homes to not burn to the ground. There's 5 nines on your house catching fire. There's 5 nines on automobile driving mileage kinds of numbers, because there are lives on the line and systems in place to get you the 5 nines. There are 5 nines on computer systems, and they're not always worth it. The military has 5 nines usages. There's people lives on the line.
Unless your name is Boeing. Maybe that's a joke too soon.
Boeing effed that one up really big. And they lost their 5 nines for that MAX plane for a very long time. Yes, sirree, Bob. Phone company used to be 5 nines. It has not been 5 nines for a long time. But when I was a kid, it was 5 nines. And you could tell it was just 100% reliable. Pick the phone up, good to go. Of course, you had a tail on the end.
What's a phone?
Well, you got a phone. Come on.
When's the last time you made a phone call with that thing?
With the landline or the phone?
Or either with the phone.
All the time. Yesterday. An actual phone call. Yeah. I don't know what you mean by you're thinking about texting.
No, like phone. No, well, yeah, it's like texting or video calls or Slack or many
My wife
things.
is driving her car and she's trying to tell me when she's home for dinner. She called me, I called her. Hands on the wheel, hands free, can't text, can't look down, can't video phone, but you can voice call.
It's like you're over 30.
You would think so. Wow. Strange world. And yet, there's a whole lot of systems that work because people over 30 thunk it through.
I might be the odd exception there. I don't have data on my phone. I actually.
Excellent.
Well, I don't really text you. I do use dedicated apps for it, but that's mostly from a privacy perspective.
I got data, but I got data because of Google Maps.
Yeah, I'm that type of person who plans his routes before he leaves on a piece of paper. And I do that mostly for liability reasons. Like I've been bitten a few too many times where I would go somewhere and I'd have, say, my map loaded on my phone, or I would have data, and there would be no signal, or it wouldn't load, or whatever. So like, no, piece of paper has 100% reliability, unless I, throw it in water or set it on fire.
Yeah. Yeah. Well, I certainly carried my paper maps for a long time after Google because of those failures. Google finally got the whole download a map ahead of time. So I go travel to Europe. I download the map in my desk, here. But if I'm going outside the zone, I'm grabbing paper maps. Yeah, absolutely. I still know how. My kids do not know how to use paper map. Oh no, I taught my sons how to use paper map. We drove, when buying the house I'm in now, I had to sell my old house. We had no house to live in for like a 3-week window. So I took my 2 sons who were otherwise at home with me, and we drove across Canada. And I taught the older one to drive on the Trans-Canadian Highway. And the younger and the older one both learned how to navigate on a paper map through the Canadian wilderness. So there you go. Not claiming they can use one now, but they certainly got the lesson.
You young kids with your fancy compasses.
Exactly. In my day, we looked at the stars. Can't see the stars in San Jose.
There's only one highway in Canada, so that's not really much of an accomplishment.
No, teaching your kid to drive on these crazy mountain roads, that's something.
It's like,
Yeah, the mountains are a little more challenging, but the prairies are kind of flat and the roads are pretty straight. You can sleep for half an hour on one of those. And
we started on them prairies, yeah.
Yeah.
But they crept up into the mountains, and we went through like Banff and stuff. We went way up in the Rockies.
way up in the Rockies. Oh, you went through my neck of the woods then.
We ended up through Michigan or Minnesota. We went to Glacier National Park, straight north on a highway that was more than just not the Trans-Canadian, because it went straight north. Turned left at some town that I could find on a map I don't remember the name of, and went to all the way to the ocean, basically.
Timmins.
Down through Victoria and Vancouver.
You turn lake at like, oh, there's the Ste. Marie or Timmins, right?
Those sound familiar, but I don't remember now.
There you go.
It was a good, fun, high altitude, high summer drive. We had, daylight for 20 hours a day and whatever. It's like, go to sleep at night.
So getting out of where I am right now is quite fun because if you go that way, you have to hit 1,700 meters before you can get out of town. And then you go out in this direction, I think you're at about 1,300 meters before you get out of town. And if you head down south, then yeah, you need to be well over 1,000 meters before you get out of town in all three directions. So when we get a snowstorm here, then they close the highways, you're just not getting out unless you're on a plane or something. It's crazy.
Yeah, I'm trying to do meters to miles conversions.
1,700 meters is more than a mile.
Yeah, see, in Houston, where I grew up, you can drive on I-10 at a straight line at 70, 80 miles an hour for 2 hours and still be in Houston. There's a scale problem there.
But it makes up for it by being the ugliest city in the world.
It is the ugliest city in the world. And it's in a swamp just to help keep the theme rolling. And the mosquitoes are amazing. Cockroaches, the flying cockroaches are that big, and
the fires never stop. The refineries.
Oh, the refineries. Yeah, the refineries never stop. Yeah, but I say it's a swamp. Things don't burn unless you try hard.
Well, I meant the belching black
smoke. Oh, the belching
fires coming out of the refineries.
The Houston Ship Channel has an infinite number of belching
make
fires.
You cry.
Right.
Gotcha. They had some cool art. The oil companies poured money into like major museums and stuff. You can get some cool stuff downtown. And people have like closed downtowns in big major cities for freezing weather in the winter. In Houston, it's closed and air conditioned. You go around outside on the city streets, on the sidewalks, they're big, wide open downtown, no one on them. It's way too fucking hot. You go down below, and there's subterranean, complete downtown is tunneled for being air conditioned. It's a whole nother world.
Yeah, I'll change my background.
Fine. All right, are we done? We're off into talking about weather in old towns. And
I whipped up the example of what I was talking about last week, if you want to see that.
Oh, sure, bring it on.
Yeah.
Yeah, the last point on weather before I got to blow out here is that today they said it's the first time that Canada has been below freezing in every part of the entire country in the last 100 years.
Oh,
Sorry.
interesting. Yeah. Okay.
Well,
Well,
some climate change on there.
it's a giant big
Freezing
place.
here today.
Huh. And it's a lot of ocean, which would be moderating freeze. That's interesting. Okay.
Yeah, and the jet stream usually keeps things like Victoria like well above zero.
So I'm about to say some of these places, right. Jet stream comes wandering around and messes reliably. Oh, screen share enabled. Sorry, Cameron, just say it. I'm so clueless.
You guys are having such a nice conversation.
Right.
Try it now.
What are you showing there, Cameron?
Nothing yet.
Or what is he attempting to show?
He had a thing we were talking about last week. Well, we talked about lots of things, so I don't remember.
Yeah.
Oh God, it looks like.
Try this. All right, how's that coming through?
It looks okay. Derived base foo.
It's too clear.
Yeah, so this simple example. Remember I was talking about the capped concept?
Oh.
So this is the, this structure here is used both compile and runtime. This is basically the roadmap. This is the Google map of the code.
So your int foo overrides a void foo in base. Is that intentional?
Yes, in this case, yeah, I was actually trying to show that. So you can add
Like covariant return types here.
Sure. So the what I wanted to show though, so this is the the derived class.
Yeah.
And so what you see here is that the where is it? Foo. So this is the foo. That's the method chain. So you see there's two methods in the chain. And then there should be, where is it? Wait, here's method derived foo. That's the void foo. And then there's also the int foo, which is a chain. Just see if there's a cap.
But how do you tell which one you're going to get?
Oh, the compiler picks it.
Well, right, but why is he picking a void foo from an int foo?
Yeah, how do you know which one the compiler is going to pick?
Yeah.
How do you tell the compiler which one to pick?
So either way, it's executing this one.
When you're calling a derived. Yeah, fine.
And then if that were to super, it would end up here either way.
And it wouldn't give you an int back. The super's known not to be an
But
int.
the thing is, there are things compiled against the void foo signature.
Yeah.
So you don't want to drop the void foo signature and then have to patch that back together later. So what you end up here is with two columns, if you will, two signature columns that show up. I had some better examples too. That shouldn't have been the first example, but this one I'm trying to make a little more complex, where I'm showing a.
Is that going to dispatch based on the return type then?
Sure.
Multi-argument dispatch. But you can't necessarily, how do you infer the return type, or you don't infer return types?
We do. Yeah, we have full type inference, including return types. Yeah. So yeah, you can actually have two different methods that have two different return types, and it'll dispatch based on what you're looking for. So in this case, I was trying to show some. This has the mix-in example. So basically, there are three different ways that I'm going to end up using the mix-in. Well, actually, more. I can mix it into base. I can mix it into derived. Or in this case, I can apply the mix-in in the class composition itself to make a derived too. Or here, I can apply it on the other side of the door. So instead of wrapping it around, So what this one does is it wraps the mixin around the composition. And in this case, the mixin is actually incorporated inside the composition. It's a subtle difference. It just has to do with method chain ordering.
So slow down.
Stare for a while.
So I'm trying to understand what problem this solves.
We were talking last week about where do you put the V table with a pointer? And one of the notions was you have a fat pointer and the V table information is kept with the pointer. And at sites where in Java you would flip from a standard object hierarchy to an interface, you could replace the pointer's V table with the interface, do your lookups with that, but the pointer still retains its base object notion somewhere indirectly through the pointer. So there are two different V tables in play, one of which is the base objects and one of which is the interface of the moment that it's currently being treated as.
Yeah, and what I was trying to show here is two different types of operations that are not arbitrarily ordering composable, right? If I'm adding and multiplying, it kind of matters which order I do it in. So, so if I add and then double versus double then add, in one case I get an odd, in the other case I get an even.
Well, right. So the question now is, what is super that doing? In the class derived, super goes to base, gets you a 0 back, you add 1.
That's correct.
In mix-in doubler, super that goes to base, but it's a mix-in. So mix-in is your interface-like thing?
Mix-in is a mix-in. It has a plug. Its plug is called base. So anything that's a base, I can plug that mix-in into.
Okay.
So, for example, if I do create an at
So-
doubler derived.
Can I abuse your terminology slightly here and
Sure.
say mix-in doubler is as if in the Java world, it's interface called doubler, but it's tied to a base.
No, it's actually a subclass, but it doesn't know who its superclass is, if you want to explain it in terms of Java.
Okay. Yeah, fair enough. Okay. Yeah. I'm very, very, okay. I was trying to, yes.
It's a subclass that can be subclassed onto anything that is a base.
Yes. Gotcha.
So it's called a mix-in, or some languages call it a trait.
Yeah.
So for example, I can create a new doubler base. I can create a new doubler derived. And if I create a new if I say new at doubler base, then foo returns 0 because it's 2 times 0, right? One other thing, super is not the same. So in Java, super is a keyword. Here it's a reference of type function. So this is actually, so I could actually take super and return think of super as a function pointer. Its type is, in this case, function of whatever well, here, let me show you. So if I look at the underlying info for these, so the base class is not surprising, right? Except in one way. What would I call it?
I think you're better off sticking with the text, not the dump, in terms of trying to explain what's going on, because we're not going to be able to read the dump very well.
All I'm trying to show is that the method foo here has one function in its function chain. So if you think of it as a V table, it has a pointer to that 0, and that 0 doesn't have a super. So there's no next in the list, right? So if I were to say something here like super, that would be a compiler error because there's no super defined.
Yeah.
Right. So
what do you get if you call super in a Java lang object? Well, you can't write any Java lang object code, so you can't write it in Java, but that's the concept.
Right. Well, and our object's a little bit different.
Yeah, don't worry about it. Don't too many things. Go back.
It's an interface anyway, so it's not.
Yeah. Like I said, too many things. Go back. All right, so we're trying to sort out is mixing symmetric or not. So go back to the prior code. So I think I at least am good with base and derived, and I'm mostly good with doubler, except now we have to use doubler in a sentence. So then line 73, doubler is mixed into derive to, which extends base.
So when we compiled this,
yeah,
what comes out of the compiler is a composition that has doubler wrapped around this class, this subclass of base. So
okay.
Can you say
doubler supers
like
to
an
derive
interclass?
2 goes to base.
Doubler goes to derive, 2 goes to base. Correct. Sorry, Kirk, what was that?
Oh, doubler goes to derived,
2.
and derive 2 goes to
Derive
base.
2.
Yeah.
And derive 2 goes to base.
Okay, so when you say wrap, I was thinking like, is derive 2 actually like an inner class of now doubler, or doubler like an inner class on derived?
So in this case,
or neither?
When I refer to, if I said new derive 2, what I would actually get is that composition that starts with the mix-in as a subclass, if you will, of derive 2 as a subclass of base.
So now follow the super chain here in foo on derive 2.
So if I do a new derive 2 and I call foo, it will first go to doubler, which supers to this implementation, which supers to the base implementation.
Okay,
so
when you
0,
call new derive 2 and you call foo, where is the implementation? It's the line 67 implementation gets run first?
That's correct. Line 69. Yes, that's correct. It does doubler.
So it's going to do 2 times the super, which then goes to the derived 2's, which is super plus 2, which then goes to base.
Correct.
So unwinding, it returns a 0 to the derived 2 super at line 79, adds 2, gets a 2, returns to the line 69, which 2 times 2 returns a 4.
Correct.
Okay, I got that you added a leaf subclass below derived 2 with the mix-in. That was an interesting change. Okay, fine.
And then just the third example here.
All right. Too deep for me. I need to roll.
And this, you're saying you jam doubler inside. So derived 3 supers up to doubler.
So this one runs first. 3 plus 2 times 0, which is 3 total.
Right.
If it matters.
So you're basically declaring your mix-in as a trait that can be put before or after the class that uses it.
Right.
Huh.
So
sorry, go ahead.
I'm still I'm looking for an answer to my earlier question. What is this good for?
Yeah, well, I was coming around to that one.
Well, these examples aren't very good for anything, but I can tell you that we actively...
this distills it into the kind of its essence. But somebody building an application would use this to do what? Or
would use which aspect of mix-in?
Well,
I'm using a mix-in. Why am I using a mix-in in the before case? Why am I using the mix-in in the in between case? What is the goal? What is the, show me a poster child case where a mix-in's just the right thing to do.
That's a good one to pull up.
Doesn't that just come down to it's a multiple inheritance solution?
Yeah, that's what I'm right. It's a
course.
multiple inheritance solution, and
yeah, but we've got 2 styles, and why do we need both? And
right. You could clearly make a bogus class after doubler that put the mix in, and then doubler 2 would go to that mix in. You could make it go without having syntax that let it go ahead or behind. So like I'm saying, pick one that has an obvious, this is the right thing to do with the mix in, like mix in debug.
Right. So I'll give a quick example. How's that? Let's just do this. So lazy is probably one of my favorite examples of a mix-in. So here I have a mix-in. It's called lazy var, and it mixes into anything that's a var. Okay.
And
so
a var is, I don't know what a var is.
Int x is a var.
Okay.
whether it's a
Okay.
property on a class or whether it's a variable in your
This sort of
method.
wraps a future around it.
No, future is also a mix-in, but
Okay.
this is a lazy. So basically, what in this is actually the. Let me just move my window thing here so you can see it. That's actually how we do lazy calculations. So what you think of as a property on a class, if I declare it as lazy, I can tell it, to calculate its value, right? And that could be a property of. There could be any one of a billion different properties of a billion different types, right? So I don't have to.
This is
So
an
is it mostly
implementation
used
of
for containers?
lazy.
Sorry, there were two questions at once. What was
I was
it?
just going to ask if this was an implementation of lazy final fields, basically.
Yes. Yep.
Okay.
That's what you see here is that when it sets it, it makes sure that it hasn't already been assigned, and it makes sure that it is assignable. So this assigned property is a property of a read-write variable, and the assignable is just a local private property on the property.
Is that assert executed every time at runtime? Is it a
That's
runtime?
correct.
It is
It's
a
a
runtime.
runtime assertion.
So it is not a compiler error to lazily reset a final. It is a runtime error to second. That is checked at runtime with a Boolean flag test.
Sorry. Well, we don't have final in the Java sense.
Yeah.
We have immutable objects.
Yeah.
So with an immutable, it's a runtime error to try to change an immutable object.
Okay.
And if it's known to be immutable at compile time because it's an immutable type, then it's also an error at compile time.
So what makes this a lazy var and not a lazy val if it's a value that's supposed to stay the same once set?
I'm not sure I understand the question. So
It seems like it's lazy, but once it appears, it's a value, not a variable.
oh, correct. This is a lazy var because it's a mix-in into a var. So the implementation of this is a variable. This is a variable. It just only allows itself to be set once.
Right, but it requires a runtime test to validate that it's only set once.
Correct.
Yeah.
Correct.
Okay. Set once variable with an assertion, a runtime assertion that in fact it was only set once. Fine.
Right.
And you would like to believe there's compiler optimization under the hood at some point that declared that you could type flow and realize it was only set once and get rid of all the runtime checks that it's only set once because you knew it was only set once or whatever.
Sure.
Yeah.
But that runtime check will only run once.
Yeah. Yeah. It's fair enough. Fair enough.
That's the other thing. Yeah, you only pay on set.
Right.
From that point.
So yeah, maybe it's all good.
So that's a mix-in. I mean, that's an example of a mix-in. I mean, I can show you more complex ones, but I'm afraid that I'd be skipping ahead 10 chapters in the book, if you know what I mean.
Yeah.
So,
Well, all right, we're like well along, and I have a noon thing, so I'm going to declare victory here, I think.
I'll come up with a better example next time. How's that?
Yeah, I mean, fun stuff, but it's also learning for everybody, and it's actually hard to make these things like understandable and shareable in short notice. It's like a thing. Links to Familia. So Matt's busy again. Okay, there's more stuff in the chat. I'm going to click through it, but I'm going to declare victory. Unifying interfaces. Yeah. I'm playing my own unification game right now. It'll be interesting to see how far we get. Okay, well, this was good. Hope to see everybody next week. Have a great weekend. Bye-bye.
Bye, guys.
Cheers.